learn about the errors of the gyro compass. We have seen in the concept and working of the gyro compass that it is based on a free gyroscope which is gravity controlled, and its circular motion turns into a elliptical motion, and then it is damped, in which the elliptical motion converts into an inward spiral, and eventually it settles down and gives us a fixed directional reference. But the settling position of the gyro may not be exactly in the meridian, or in other words, the gyro may not show us the true north. This is because of some of the errors which may come in the working of the gyro compass. So we are going to understand what these errors are, what are the causes of these errors, and how these errors can be calculated and eventually rectified or compensated. So discussing on the same lines, the headings or the directions given by the gyro compass have some inherent errors in them. The most significant of these errors are: number one, the settling error, also known as damping error and also known as latitude error. The first error which we are going to discuss is represented by these three names: the settling error or the damping error or the latitude error. The second most significant error of the gyro compass is the course, latitude and speed error, in short known as CLSE, C for the course, L for the latitude, S for the speed, E for error, and it is also known as steaming error. Now the second error which we have gets its name as steaming error because this error is present in the compass only when the ship is moving or steaming. If the ship is not steaming and is stopped, in that case the second error is absent. It is not there. That's why the name given to it as steaming error. So starting off with our first error, which is known as the settling error or the damping error or the latitude error. Now, why is it called a settling error? Because this error is caused because of the settling process of the gyro compass. We have seen that a gravity controlled gyro is damped. Its motion converts into an inward spiral, which you can see in the diagram on the screen now. And because of this settling process, the error is generated. That is why the name given to it as settling error. It is also known as damping error because it's a byproduct of the damping which we have done in our north-seeking gravity-controlled gyro compass. It gets its name as latitude error also because this error is dependent upon the latitude of the observer. If the observer is on the equator, which means the latitude is 0, in that case the damping error, settling error or latitude error is also 0. As the latitude keeps on increasing, the error also keeps on increasing in magnitude. That's why the name given as latitude error. Now we have seen the inward spiral motion of the damped or north-seeking gyro compass, and in this damped motion or spiral motion we saw that our spin axis eventually settles in the position which is right now. You can see the laser pointer is exactly highlighting and showing that position where the gyro spin axis settle, the position S. Now this position is the one where all the four forces which are acting on our spin axis or the gyro compass. These forces are mentioned here. That is the tilting represented by the red arrow, drifting represented by the blue arrow. Both of these were caused because of gyroscopic inertia, because our gyro spin axis was following the motion of the gyro star. And the control precession represented by green arrow, damping precession represented by the yellow arrow. Both these, that is the control precession and the damping precession, brought in by us to first control the motion of the free gyro and then later on dampen the motion of the free gyro to make it north seeking so that it settles down at one particular location. So under the effect of these four forces, our spin axis settles at this particular point, which is point S. Now this is a point, if you look carefully, where all these four forces are balanced out. You have the blue arrow drifting in the easterly direction, and you have the green arrow, that is control precession, in the westerly direction, exactly equal and opposite to each other. You have the representing the tilting upwards, and you have the yellow arrow representing the damping precession downwards, both exactly equal and opposite to each other. Now, if you look carefully, this settling position is not in the meridian. You see, the vertical black line shown by the laser pointer in the diagram now, this vertical black color line is the meridian, and our gyro has settled at point S. Now it is not in the meridian, it is slightly east of the meridian. The right side in our diagram is the east side. The left side in our diagram is the west side. So you can see it has settled down slightly east of the meridian. Now this difference represented by the maroon color double arrow in the diagram, this particular difference between the meridian and the position where the gyro compass settles is our first error, the settling error, damping error, or latitude error. Now let's try to understand the cause of this damping error. Now we are aware that for any particular latitude except the equator, there will always be some amount of drifting. Now drifting, we are aware of the drifting formula. It is given by 15 degrees sine of latitude per hour. And you can check from the formula also that at the equator where latitude would be 0, the value of drifting is going to be nil. There will be no drifting at the equator, but if you are on any other latitude other than the equator in the north or south hemisphere, there is going to be some drifting value as per the formula. Now, we have to counteract or cancel this drifting by control precession. So as you can see, the drifting in this diagram is acting in the easterly direction because we are in the northern hemisphere. The drifting direction is easterly in the northern hemisphere. So we have to cancel or counteract it using the control precession. You see the green color arrow, which is counteracting or cancelling the drifting. Now, why we need to cancel the drifting? Because we want our spin axis to settle down. If the drifting is not cancelled or counteracted, the spin axis will keep on moving in the easterly direction under the effect of drifting. So we have to cancel it or counteract it by control precession. Now, control precession is proportional to tilt. So control precession can only be generated if there is some tilt. We know from the control precession formula, control precession is proportional to tilt. it is in the westerly direction down. Now, in this particular case, the drifting being easterly, we require a westerly control precession. So a westerly control precession can be generated only when the spin axis is tilted upwards. As you can see in the diagram, this black color horizontal line highlighted by the laser pointer is the horizon. It is labeled here in the diagram, and you can see our settling position in this case is above the horizon. So the tilt is up. This upward tilt generates a westerly precession, which cancels out the easterly drifting and eventually helps us to settle down the spin axis of the gyro. So for this control precession to be generated, we need to have a upward tilt. Now for generating some amount of tilt, we require the tilting motion. The tilting motion is what generates the tilt. So tilting motion needs to be there. Now from the tilting formula, we are aware that tilting is only possible when the spin axis is not in the meridian. Or in other words, tilting can only occur when the spin axis is off the meridian, because tilting at the meridian is nil. The formula for tilting involves sine of azimuth. So 15 degrees sine of azimuth cos of latitude. So if the spin axis is pointing in the meridian, the tilting would be 0. If tilting is 0, there will be no tilt generated. If there is no tilt generated, there will be no control precession. So we need some azimuth for tilting to be present. Now, since some azimuth is required, because of this reason, the spin axis of the gyro settles off the meridian and slightly tilted, where all the forces balance out. Now I need to generate westerly precession to counteract the drifting. Westerly precession is generated when the spin axis is tilted upwards, when there is a upward tilt. Now upward tilt is generated when the tilting motion is upward. Now tilting motion is upward. We know from the tilting formula that tilting is upwards east of the meridian and tilting is downwards west of the meridian. So this is exactly the reason why in this case the spin axis has settled east of the meridian. So you can correlate to this in the diagram. Pay attention to the laser pointer. I'll explain it to you here. The blue color vector showing the drifting, the green color vector showing control precession, which is equal and opposite to drifting and is counteracting it. To generate the westerly precession, the spin axis needs to be tilted upwards. So you can see we have the horizon here and our settling position is upward of the horizon. So we have a positive tilt which generates this westerly precession. Also, you can see that tilting is exactly equal and opposite to the damping precession, which is the yellow arrow. So basically at this position, drifting is equal to PC, control precession, and tilting is equal to PD, the damping precession. The position is slightly above the horizon and east of the meridian, as we see in the diagram. And if we go to south latitude, the spin axis settles slightly below the horizon and west of the meridian. So I hope it is okay up to here, beta. Clear? Now, one important thing to understand and keep in mind is that this particular error, that is the settling error or damping error or latitude error, occurs only in the gyro compasses which are damped in tilt. We had seen that there is two types of damping which is possible, Either the compass can be damped in tilt or the compass can be damped in azimuth. Now, this error is not present in compasses which are damped in azimuth. This is only present in the gyro compasses which are damped in tilt. Keep this in mind. This fact is used in the numerical sometimes. When they provide you a numerical, they mention to you whether the compass is damped in tilt or damped in azimuth. And accordingly, we have to see whether the settling error will be present in that compass, damping error will be present in that compass or not. Now, let us see the derivation of the formula, how the damping error formula is derived, and it helps us to calculate the exact value of the damping error. Now, we just saw that at the setting position, drifting is equal and opposite to control precession. So the magnitudes are equal and the directions are opposite. And also tilting is equal and opposite to damping precession. You can see the blue arrow representing the drifting is equal and opposite to the green arrow, which is the control precession. The red arrow, which represents the tilting, is equal and opposite to the yellow arrow, which is the damping precession. Now we are aware of the drifting and tilting formula. The formula for drifting is 15 degrees sine of latitude. Since it is equal and opposite to PC, we get this relationship or equation number 1. Drifting is equal to control precession, or 15 degrees sine of latitude is equal to PC. Exactly in the same way, since tilting is equal and opposite to damping precession, tilting is given by 15 degrees sine of azimuth cos of latitude. It is equal to the damping precession, which we represent as PD. Now we have these two equations in front of us. What we are going to do is we will divide the equation number 2 by equation number 1. And as we do it, we get the relationship 15 degrees sine of azimuth cos of latitude divided by 15 degrees sine of latitude is equal to PD upon PC. 15 gets cancelled in the numerator and the denominator, and we are left with the formula sine of azimuth. This value is kept on the left hand side, is equal to PD upon PC, PD upon PC, and you see the cos latitude upon sine latitude is taken onto the right hand side of the equation, and when it goes on the right hand side it becomes sine lat upon cos lat, which converts to tangent of latitude. So we get the relationship sine of azimuth is equal to PD upon PC into the tangent of latitude. So this is the relationship which we have got. Now the ratio of PD to PC. PD is damping precession and PC is control precession, is also known as the damping ratio. And this ratio is constant, represented by alphabet K for any particular compass. So for a compass which is fitted on a ship, this ratio, the damping ratio PD upon PC, is fixed and constant. The Sperry make compasses are having this ratio exactly matching to 1 is to 40. So how is this 1 is to 40? Let me take you back a little bit. When we discussed about the concept of the gyro compass, I told you there are two weights which are fitted on a gyro compass. One weight, the bigger one, is used to make the compass top heavy. Now that weight, if you remember, is 680 grams. The most effective weight which can be used to control and dampen the gyro, an 80 grams weight, which is used to make it top heavy. Now there was another weight which we used to dampen the compass to make it north seeking, to make the motion an inward spiral, and that weight was 17 grams. Now the top heavy weight 680 grams is what generates the control precession, and the small weight which is 17 grams is what generates the damping precession. So 17 gram is to 680 grams is exactly the ratio of 1 is to 40. 17 fours are 68. So 17 grams to 680 grams is this ratio of 1 is to 40. The damping precession, which is generated by the smaller weight, 17 grams weight, proportional to control precession, which is generated by the bigger weight, which is 680 grams weight, gives you a damping ratio of 1 is to 40. Now, when we use this 1 is to 40 ratio, the formula converts to sine of azimuth is equal to k tan latitude. PD upon PC is replaced by k, where k is equal to 1 by 40 in Sperry compass. Now, in other makers also, you could have a Tokamak compass or a Anschutz compass. In other makers also, the ratio is kept very close to 1 by 40. It could be exactly 1 by 40, but it could vary a little bit. In some case, it could be 1 by 39, or in other case, it could be 1 by 41 also. But the ratio does not go too much off from this 1 is to 40 figures. Now, as far as our questions are concerned, if the damping ratio of a compass is provided to us in the question, we will use that value which is provided. They may either provide this information to us straight away, telling that the damping ratio of the compass was 1 is to 40, or they may give us some information with which it can be easily calculated. So in both these cases, when it is directly provided or some information is given with which it can be calculated, we use the given value. But if in some question the damping ratio is not provided to us, we use this ratio of 1 is to 40. So if you need this for your calculation and it is not given to you in the question, it is to be considered and taken as 1 by 40 ratio. Any doubts up to here, beta? You use this damping ratio and you use this formula. The azimuth what you obtain here is nothing but the settling error. As you can see in the diagram, the azimuth here is what the difference between the meridian and the spin axis is. The azimuth basically tells you what is the direction in which the spin axis points. So whatever azimuth you obtain from this formula, this azimuth is your damping error. So let's summarize the formula now. Sine of damping error is equal to k into tangent of latitude, where k is equal to 1 by 40 if not given in the question. Now this formula is going to give you the magnitude of the damping error. It will give you the magnitude of the damping error. Now we also need to find out whether the damping error is easterly or the damping error is westerly. Now, as we just now discussed in the explanation in the previous slides, that the compass always settles east of the meridian when you are in a northerly latitude. So that is the reason the error is easterly on northerly latitudes. If you are in the northern hemisphere, the damping error will be east. Now, an easterly error is also known as low error. In fact, in case of the gyro, the low and high format is more frequently used to indicate the error of the compass. East and west is more frequently used in case of the magnetic compass. But both these terms are interchangeable. You can denote the error as east or you can denote the error as low. Now this can be easily memorized by remembering the idiom error east, compass least. So it tells us whenever the error is east, the compass will be least or the gyro error will be low. And whenever the ship is in southerly latitudes, you are in the southern hemisphere, the error will be west because the spin axis in that case settles west of the meridian. So westerly error is also known as high error. So we are aware of the idiom error west, compass best. So you can represent it as westerly error or you can represent it as high error. Both are interchangeable. So error is low or east in the northerly latitude. Error is high or west in the southerly latitudes. So this summarizes the damping error formula. So very important formula. And this is what the questions on gyro compass, numerical questions on gyro compass are based upon. The questions which we get in the exams are based upon the gyro errors. And this is the first important formula for the damping error. There are only two formulas here for gyro numerical. One is this one, which you are seeing on the screen right now. The second one, which we are going to discuss, is the formula for CLSE or steaming error. So this completes the explanation of damping error. Now moving on to the second significant error of the gyro compass, which is the course, latitude, and speed error, in short known as CLSE, and the second name for it is the steaming error. Now why it is called as steaming error? This is because it is generated only when the ship is steaming. This when the ship is stopped, the error only appears when the ship is moving. The second thing is that this error is independent of the design of the compass. We saw the damping error was based on the design of the compass, but CLSC or steaming error is independent of the design and is present in all type of compasses in case the ship is moving. Now, what is the cause of this steaming error? Now, we have seen in the explanation of the gyro compass, a free gyro is controlled and then damped to make it pointing towards north. We use the control precession to control the free gyro, convert it into elliptical motion. We use the damping precession to make the gyro north seeking, converting it in an inward spiral motion and eventually settling it down. Now the gyroscope pointing towards the north direction is actually aligned in a direction which is perpendicular to the direction of rotation of the earth, which is easterly. Now to us it appears as if the spin axis of the gyro compass is pointing in the northerly direction, but there is a catch to it. You can view it from a different perspective. Actually, the spin axis of the gyro is pointing in a direction which is perpendicular to the direction of rotation of the earth, which happens to be the northerly direction. You can easily understand it from the basic concept of the gyro compass. You see, the gyroscopic inertia was responsible for making the free gyro moving in circular motion following the motion of a star. Now, if you go to the basis of it, why does the star appear to move in a circular motion? This happens because of the rotation of the earth, because the earth is rotating on its axis in the easterly direction. So the basis of the entire motion of the free gyro is actually the rotation of the earth. By using the control precession and the damping precession, we have made such a arrangement that the spin axis points in a direction which is at right angles or perpendicular to the direction in which the earth is taking us, that is the easterly direction. Now the gyroscope pointing in a direction perpendicular to the direction of rotation of the earth works very well as long as the gyro is kept stationary. The gyro is not moving, the gyro is kept stationary. So it is able to sense or judge the direction in which the earth is rotating, and it aligns itself perpendicular to that particular direction, which happens to be north, and we get a directional reference. But the entire scenario changes if the gyro is placed on a moving vessel. Gyro is placed on a ship which is having a motion of its own. Now, once the gyro is placed on a moving platform, a moving ship, or any vehicle or a plane, the gyro then senses the resultant of the Earth's east-west motion and the vessel's own motion as the actual direction of rotation of the Earth. So what happens now is, see, the gyro doesn't know where it is placed. Gyro doesn't know whether it is stationary or whether it is placed on a moving ship. The function of the gyro is to point in a direction perpendicular to where it is being taken in space. Till the time the gyro was stationary, Earth was taking it in exactly easterly direction and it was pointing at right angles to it, which happens to be the northerly direction. If the gyro is placed on a moving ship, now the ship is moving, the Earth is moving. As viewed from space, if you have a look at the motion of the ship, you see it has got two components now. One is the rotation of the Earth, and second is the motion of that particular ship. And in space, or with respect to space, if you have a look at the motion of the ship, it will be the resultant of both these components. Now the gyro senses the motion of this resultant and the gyro aligns itself to the resultant. So gyro senses the resultant of the Earth's east-west motion and the vessel's own motion as the actual direction of rotation. It is basically the actual direction in which the gyro compass is being taken with respect to space. And then it aligns its axis perpendicular to this resultant. So this is the reason for generation of the steaming error. We will understand it from the diagrams also, where it will become more clear to you in the coming slides. Now let's go into the formula for the CLSE, the course latitude speed error or the steaming error. You can see the formula on the screen now. Tangent of CLSE, that is course latitude speed error, is equal to V cos course. V is the speed of the ship and course is the course which the ship is making good. Whole divided by 900 cos latitude plus minus V sine course. So latitude is the latitude of the place where the ship is. You can see two signs mentioned here in the denominator, a positive and a negative sign. We will see which sign is to be used as per which criteria. Then you have the V, which is the speed of the ship, sine of the course. Now the course which we use in this formula, the course which the ship is making good, is used in the quadrantal notation. So it will never be greater than 90. We do not use it in the three-figure notation. We use the course in the quadrantal notation. Now, this positive and negative sign which is mentioned in the denominator, positive sign is used when the ship is moving on any course which is having a easterly component, which basically means the ship is moving in the northeast quadrant or in the southeast quadrant. And the negative sign is used when the ship is moving on a course having a westerly component. That means the ship is moving in northwest quadrant or the southwest quadrant. So whether the ship is moving on a easterly course or a westerly course decides whether we will be using plus or minus sign in the denominator. Now, why it is a plus for easterly course? Just to give you an example here, it will become clear when I explain it to you using the diagram. But just to give you an example here, you see this first factor in the denominator 900 cos lat basically represents the motion of the earth at any particular latitude. We know at the equator the earth is taking us in the easterly direction at a speed of 900 miles per hour or 900 knots. And at any particular latitude, if you want to calculate the speed with which the earth is taking us in space because of the rotation of the earth, it is given by 900 cos latitude. Now, if the ship is moving in the easterly direction, that means the motion of the ship is adding up to the motion of the earth. That's why we have a plus sign in the denominator. And if the ship is moving on a westerly component course, that means the ship is moving opposite to the direction in which the earth is taking us. And that's the reason for a negative sign. It will become more clear to you when you see the explanation with the help of a diagram, which I will do in the coming slides. When we apply this formula, we will be able to calculate the magnitude of the course latitude speed error or the steaming error. Now, how to find what is the sign of this error, whether it is east or west, or in other words, whether the error is low or high. Now, this is checked by the northerly or southerly component of the course. The error will be high or west on northerly courses. That means whenever the ship is moving on a course having a northerly component, it could be in the northeast quadrant or northwest quadrant, the error will always be west. It is also called as a high error. And whenever the ship is moving on a course having a southerly component, that means the ship is either moving in the southeast quadrant or the southwest quadrant, it decides that the error will be east or low. As we discussed earlier, the west error can be denoted or significant or represented by high. They both mean the same thing. These are interchangeable. You can say the error is west or the error is high. And similarly, low and east, they are interchangeable. They mean the same thing. You can remember them very easily using the idioms error west, compass best. If the compass is best, that means the gyro error is high. And error east, compass least. If the compass is least, that means the error is low. So thus the formula gives us the magnitude of the steaming error, the course latitude speed error, and it also gives us the sign or the whether the error is low or high. So this is the second important formula in gyro errors. The first one which we saw was for the damping error or settling error. Now you need to be careful about the direction in which the ship is moving. The easterly and westerly component of the ship's course decides whether we will be using a plus sign or minus sign in the denominator. And the northerly or southerly component of the course decides whether the error will be high or low. So you need to be careful about both these conditions because sometimes candidates get confused which component is used to decide which of the factors. Okay, so always remember the easterly and westerly component decides the sign coming here in the denominator, and the northerly or southerly component decides the sign of the error, whether it will be east or west, low or high. Try to understand the derivation of this formula, how this formula has been derived, and it will also give us a better insight into the course latitude speed error or the steaming error. Now we can easily understand it using a diagram. You see the diagram on the screen now. This diagram is very helpful in understanding the derivation of the course latitude speed error. It looks a bit complicated in the beginning, but once you understand each and every part of this diagram, it will be very simple to derive this formula for the CLSE. So let's try to understand the diagram. Now, first of all, concentrate your attention to the red color vector shown in the diagram. You see the red color vector, which is highlighted by the laser pointer, alpha to delta. Now this alpha to delta vector represents the Earth's rotation. And you can see here, this is mentioned as 900 cos latitude, which is the factor which gives us the rotational speed of the Earth at any particular latitude. So the red color vector alpha to delta represents the rotational motion, rotational speed of the Earth at any particular latitude. It is denoted by 900 cos latitude. We already discussed it. At the equator, the speed is 900. So if you put the latitude as 0, cos 0 factor becomes 1 and you get 900 answer. At the pole, the latitude being 90 degrees, cos of latitude, cos of 90 becomes 0, giving us the rotational speed of Earth at the pole as 0. For any intermediate latitude, the speed will be between 900 and 0. Now, if you look carefully, there is a parallelogram A, B, C, and D. This is a parallelogram. We have drawn it to find out the resultant of the vector forces. This is used for vector addition and finding the resultant. So if you concentrate your attention to the side Bravo to Charlie, this is again mentioned in red color, Bravo to Charlie. This is exactly the same vector as alpha to delta. These are the two parallel sides, opposite sides of a parallelogram. And whether it is alpha delta or it is Bravo Charlie, both represent the Earth's rotation, which is given by 900 cos latitude. Now moving further, now you concentrate your attention to the blue color vector alpha to Bravo. So alpha to Bravo, the blue color vector represented by alphabet V vector. This represents the course and speed of the ship. So alpha Bravo vector, the blue color vector represented by V, represents the course and speed of the ship. And if you go to the opposite side of the parallelogram, that is delta to Charlie, you will see that this delta to Charlie vector is exactly similar or same as alpha to Bravo vector. So both these vectors forming two opposite sides of the parallelogram, alpha to Bravo or delta to Charlie, represents the course and speed vector of the ship. And if you see now, we have made this parallelogram using the Earth's motion vector alpha delta and the ship's motion vector, that is alpha to Bravo. We have made a parallelogram A to B, B to C, and C to D. Now, whenever two vectors are added up, their resultant can be easily found by making a parallelogram and finding the diagonal of that parallelogram. Now you can see for this parallelogram A, B, C, D, the diagonal which we have is alpha to Charlie. So this alpha to Charlie is the resultant of the Earth's motion vector and the ship's motion vector. We have seen this vector addition in chart work also. So in chart work, we add up or combine the core steered and the current vector to get the CMG vector. So something very similar to that. Alpha to delta is the Earth's motion vector. Delta to Charlie is the ship's motion vector, and their resultant completing the triangle is alpha to Charlie. This is the resultant vector. So this green color vector which you see represented by letter alphabet R is the resultant of the Earth's motion and the ship's motion. Now, as we had seen in our earlier discussion also, that this arrangement of the gyro which we have made, we started off with a free gyro, then we controlled it using a top heavy or bottom heavy arrangement depending upon its direction of spin, and then finally we dampened it by putting a damping precession weight offset to the west. Now once you make this kind of arrangement, we see that the spin axis starts to point in the north-south direction. Now this direction is perpendicular to the direction in which the Earth is taking the gyroscope. The Earth is rotating in the easterly direction, and the gyroscope spin axis aligns itself perpendicular to the direction in which it is being taken by the Earth. Now in this case, the diagram which you see, the gyro compass, north-seeking gyro compass, is placed on a moving vessel. So it is not only affected by the Earth's motion vector, it is also affected by the ship's motion vector. So it is being carried, looking from space, it is being carried in a direction which is represented by the green arrow alpha to Charlie, which is the resultant of both these motions, the Earth's motion and the ship's motion. Since now it is being carried in the direction AC, the gyro obviously doesn't know whether it is on a moving ship or on Earth. The principle or the arrangement which we have made will make the gyro point in a direction perpendicular to the direction where it is being taken. So it is being taken in the direction of AC. Because of the arrangement, it starts pointing perpendicular to this particular direction. So perpendicular to our resultant AC is this vector which is representing GN. GN represents gyro north. So the gyro aligns itself perpendicular to the resultant vector R and points in the direction of gyro north. We can see this gyro north vector in our diagram. This is the gyro north in this particular case. Now we know the true north direction is perpendicular to easterly direction. The red color vector represents the easterly direction, alpha to delta. So if we draw a line perpendicular to it, you see a perpendicular line is drawn. This line represents the true north. So we can see here that the gyro is now pointing in a different direction than the true north. Gyro is pointing in the direction of gyro north. The true north which we need for our directional reference, the difference between these two, that is represented by this particular angle, which I am highlighting with my laser pointer now. This particular angle represented by small a is the error of the gyro compass. Any doubts? Seen that this particular angle here, angle A, which is the angle between the true north and the angle between the gyro north, is our CLSE. Now this particular angle A is same as angle A, which is shown here. You can follow the laser pointer. You see we have a small angle A here also. This is basically angle delta alpha Charlie. Now, how are these two angles equal to each other? The reason is that the angle between two lines is the same as the angle between their perpendiculars. We know the gyro north is perpendicular to AC, which is the resultant. The gyro is pointing in a direction perpendicular to the resultant. And we also know that the true north is perpendicular to alpha delta, which is the easterly direction. So angle between gyro north and true north, this small angle A, is same as angle between delta alpha and alpha Charlie, which is this particular angle. So if we find this small angle A or angle delta alpha Charlie, that will give us our CLSE. Now this angle delta alpha Charlie can also be represented as angle Papa alpha Charlie. So angle PAC is equal to our CLSE. If we find this angle, the CLSE is known. Now moving further, we are aware that this alpha Bravo vector, the blue color vector, represents the course and speed vector of the ship, and it is same as delta Charlie vector in the diagram. Delta Charlie vector, the blue color vector represented by capital V, gives us the course and speed of the ship. Now this vector is making an angle of small b with the easterly direction. And now we are going to break up this vector, the ship's course and speed vector, into two components. One horizontal component and one vertical component. Now at an angle B from this vector, we have the horizontal component, which is delta 2 papa. The horizontal component is given by V cos B, Victor cos Bravo. And the vertical component is Charlie papa. This is the vertical component of the vector. The vertical component is given by V sin B, Victor sin Bravo. Now this is a very basic vector resolution technique which we have followed. The component of a vector at any particular angle is given by V into cos, or that vector into cos of that angle, and the other component is given by that particular vector into sine of the angle. Now once we have understood this, now we take our attention to triangle Papa Alpha Charlie. Pay your attention to this bigger right angle triangle now, Papa Alpha Charlie triangle. Now in this triangle, pay your attention to this small angle A, angle Papa Alpha Charlie. This is the angle which we have here. Now tangent of this angle, tangent of small a, will be equal to perpendicular, which is V sin B, Victor sin Bravo, divided by the base. The base is alpha to papa, and the base is basically given by alpha delta plus delta papa. Alpha delta is 900 cos lat and delta papa is Victor cos Bravo. So the same thing is mentioned here in the formula. Tangent of CLSE or small angle A is equal to perpendicular, which is Victor sine Bravo, divided by the base, which is 900 cos lat plus Victor cos Bravo. Sine cos. So have a good look at this beta and let me know your doubts now. Give me a minute. So you can now see the summary of both these errors here. If you want, you can take a screenshot. This is going to show you all the required details at a single in a single picture. So both the errors formula, how they are to be applied, everything is mentioned. Let me know once you are done, beta.
Sir, this
We have the first question on the screen. A gyro damped in tilt has a damping error of 2.8 degrees in latitude 58 degrees south. Find the damping error in latitude 30 degrees north. Now we are aware the damping error formula is given by sine of damping error is equal to K tan latitude. So in this question you see they have given us the damping error as 2.8 degrees and they have given the latitude also 58 degrees south. So let's put these values in the formula and it gives us sine of 2.8 degrees is equal to K into tangent of 58 degrees. Now this relationship gives us the value of K as sine of 2.8 degrees divided by tangent of 58 degrees. So you see in this particular question, they have given us sufficient information that we can obtain the value of K, the damping ratio for this particular compass. Now once this damping ratio is obtained, then we can use this damping ratio to get the answer. Now the question says we have to find the damping error in latitude 30 degrees north. So again using the damping error formula, calculating the damping error in latitude 30 degrees north now. The formula tells us sine of the damping error is equal to K tan latitude. In this case, latitude will be 30 degrees. Using the value of K as sine of 2.8 degrees divided by tangent of 58 degrees, you put it in the calculator, you will get the damping error in latitude 30 degree north as 1.01 degrees east or low. As you put the value of K in the calculator, it will give you the magnitude as 1.01 degrees. And we are aware that the damping error is always east or low in northerly latitudes. The latitude which is given to us is 30 degrees north, hence the gyro error is also east or low. East and low are interchangeable. You can denote it by either writing as easterly error or you can write it as the gyro is 1.01 degrees low. So this completes our question number 1. Any doubts in this beta? Very simple question. We are starting with simple and then moving. Calculate the combined damping and course and speed error when steering 346 degrees true at 16 knots in latitude 52 degrees south. So beta, is the question clear? Any doubts in the question?
Clear, sir.
Very good beta. Now you see the question gives us the value of damping error at a particular latitude. This is very much similar to question number 1. The damping error was given to us, the latitude was given to us, and using these two, we were able to find out the value of K for this particular compass. So that will be the first step in this question also. We need to get the combined damping and course and speed error. So we need to get the damping error as well as the course and speed error or steaming error or CLSE when the vessel is steering 346 true. So the course is given to us. At 16 knots, the speed is also given to us, and latitude 52 degrees south, the latitude is also given to us. So it will be a simple application of the steaming error formula. Let's now see the solution. First of all, applying the damping error formula with the information provided. Sine of damping error is equal to K tangent latitude. Using it for latitude of 35 degrees north, which is given to us in the question, the damping error is given as 1 degrees east. This gives us sine of 1 degree is equal to K into tangent of 35, and it gives us the value of K as sine of 1 degree divided by tangent of 35 degrees. So we have obtained the value of K for this particular compass. Now using this value of K for 52 degrees south latitude. Now this is the latitude where we need to find our answer, the combined damping error and the CLSE. So first of all, we will get the damping error for this latitude 52 degrees south. So using the formula once again, sine of damping error is equal to K tan 52. Value of K is known to us now. So multiplying it with tan of 52 and taking a sine inverse will give us the damping error as 1.828 degrees. Now calculating these values, you can go up to say about 3 places after the decimal. Practically on board we use the information only up to accuracy of 1 place after the decimal. So that is the maximum resolution which may be required practically. But in these numerical questions, just to get a exact or accurate answer, you can go up to 3 places after the decimal. So we get the magnitude of the damping error as 1.828 degrees, and the sign of this damping error, you see the latitude is given to us as 52 degrees south. Now in southerly latitudes, the direction of the damping error or the sign of the damping error is west or high. So we have obtained the damping error for latitude 52 degrees south. Now in the second part, we obtain the CLSE, course latitude speed error or steaming error. The formula for CLSE is tangent of CLSE is equal to V cos course divided by 900 cos latitude plus minus V sine course. Plus sign is used whenever we are on a easterly course, a course having a easterly component, either in the northeasterly quadrant or the southeasterly quadrant, and a negative sign is used when we have a westerly component in the course. That means the quadrantal course is either in the northwest quadrant or the southwest quadrant. Now in this case, the course is given as 346 degrees true, which is a northwesterly course. So we have a westerly component telling us that we will have a negative sign here in the denominator in the CLSE formula. Now putting all the given values, we get tangent of CLSE is equal to V. V is 16 knots. The speed is 16 knots. Cos of course. So course is 346 degrees. We always use quadrantal notation course in the formula. So converting it into quadrantal notation, we get it as north 14 degrees west. So the value of V cos course becomes 16 cos 14. whole divided by 900 cos latitude, the latitude is 52 degrees, minus V sine course, V is 16 knots and the course is 14 degrees, so 16 sine 14. Now putting this in the calculator, you get the CLSE as 1.616 degrees. Now to obtain the direction or the name of the CLSE or the steaming error, we are aware that the steaming error on northerly courses is always west. Whenever there is a northerly component in the course, that means the course is either northeast or northwest quadrant course. In that case, the error will always be west. If the course has a southerly component, that means the vessel is moving on a southeasterly or southwesterly quadrant. Now in that case, the error would be east. So in this case, a northerly component of the course tells us the error to be west or high. West, CLSE is 1.616 degrees west. Combining both these errors together, since they are both of the same names, we add them together and get the complete or total gyro error as 1.828 degrees plus 1.616 degrees. The answer comes to 3.444 degrees and the direction remains west or high. Any doubts, beta, please let me know. Moving on to the next question. A gyro dammed in azimuth had the corrector for speed and latitude set at 0. The ship is doing 18 knots in latitude 32 degrees south on a course of 321 degrees gyro. Find the gyro transit bearing of a set of lights if their charted transit bearing is 177 degrees true. Now at the first instance, this question looks little difficult to understand. They are talking of a speed and latitude corrector. We don't have any such corrector in the modern generation gyros which we use nowadays on board. Now in this question they are talking about old generation gyros in the pre-GPS era when there was no GPS available on board. So that time we used to have these old generation gyros which had a corrector for speed and latitude. Basically there were two big knobs somewhere in the chart room, one of them for putting in or feeding in the speed and the other one for feeding in the latitude. The purpose of these knobs, the speed and latitude knobs, was to give a input of what is the current speed of the ship and what is the latitude of the ship to the gyro compass. You see these are the two parameters which are required to calculate the gyro errors. Whether it is the damping error or the steaming error CLSE, in both the cases we require what is the speed of the ship and what is the latitude of the ship. So these were fed manually since there was no GPS. Both these pieces of information were fed manually through these knobs. Now sometimes it used to happen that the vessel came out from a port and the duty officer forgot to update these speed and latitude in the knobs. The knobs were kept at 0. Let us say the speed was kept at 0. The ship was at the equator. Latitude knob was also kept at 0. Now the vessel has started moving. It has changed its latitude. It has gained some speed. But the duty officer forgot to adjust these knobs to update the speed and latitude. So what will happen in that scenario? So what happens in that scenario is the gyro is not aware that the speed has been picked up, the latitude has been changed. So the gyro does not apply any correction to the readings. If you adjust these knobs to the present latitude, to the present speed, what the gyro does is the software calculates both these errors, that is the damping error and the steaming error, and applies them to the gyro readings, and the readings which you get are the corrected readings. Now if these knobs are not properly set, The gyro will not be able to apply these two errors in the readings, and whatever readings you obtain from the gyro will have these errors included in them. So this is the meaning of these speed and latitude correctors. So let's try to now see the solution of this question. The first thing which is given to us is that the gyro is damped in azimuth. Now we know for the compasses which are damped in azimuth, there is no damping error. So that's why there is no damping error in this gyro compass. Damping error is only present in compasses which are damped in tilt. Also, since the latitude and speed corrector is set at 0, this means that the steaming error, the CLSE, is not being corrected, and the gyro readings will have this error included in them. So whatever readings we are obtaining from the gyro compass will have the steaming error in them, and to get the actual readings we will have to apply or take out this steaming error from those readings. Now to find the gyro transit bearing of the set of lights, we need to calculate this error. Once we are aware of what this error is, we will be able to apply it to the gyro readings and then get the gyro transit bearing of the set of lights. So we go into the formula for the steaming error, that is tangent of CLSE is equal to V cos course divided by 900 cos lat minus V sine course. Now we have a minus sign here because the course which we have is 321 degrees, which is a northwesterly course. So whenever the course has a westerly component, we have a negative in the denominator of the steaming error formula. Putting the values here, the speed of the ship is given as 18 knots. The course is 321, which is north 39 degrees west. So we have the course as 39 here. We use the course in the quadrantal notation. Then in the denominator, you have 900 cos of latitude, which is 32 degrees, minus V, which is 18 knots, sine of course, which is 39 degrees. Now, when we put these values in the calculator, we get the CLSE or the steaming error as 1.066 west or high. Now, the magnitude is obtained from the formula, and the sign of the error, that is west or high, is obtained from the fact that the course which we have, which is 321 degrees, has a northerly component. Whenever the course has a northerly component, this is a northwesterly course. So whenever the course has a northerly component, the steaming error is always west or high. Now we know that the charted transit bearing or the true bearing of the transit bearing of the lights is 177 degrees true. The gyro error is 1.066 high. So the gyro transit bearing will be 1.066 higher than the actual or charted transit bearing. So to obtain the gyro transit bearing, we add 1.066 to 177 and we get our answer as 178.066, which will be the gyro transit bearing of these lights. Next question. The spinning axis of a gyro compass, damped in tilt, uncorrected for damping and steaming errors, is pointing due north in latitude 61 degrees south. While making good a course of 165 degrees true at a speed of 20.6 knots, what will be the direction of the spin axis when making good a course of 345 degrees true at a speed of 13.3 knots in latitude of 61 degrees north? Now, at the first instance, the question looks a little surprising. Why surprising is because it is mentioned in the question that the gyro compass is uncorrected for damping and steaming errors. That means whatever heading or readings the gyro is giving us, the damping error and steaming error will be present there. But even a uncorrected compass is pointing due north in latitude 61 degrees south. Now, since the compass has these errors, the damping error and the steaming error, it should not have pointed due north. But even after having these errors, the compass is still pointing due north. So what could be the reason for it? Let's see. The
Damping
gyro
error in
compass is
CLS.
uncorrected
So
and
1 minute, sir.
CLSE. Okay, all right. Still points due north. Now this is only possible if the damping error and the steaming error are exactly equal and opposite, thus cancelling each other. Since the compass is uncorrected, damping error will be present, the steaming error will also be present, and the only way you could have a zero gyro error is if both these errors cancel out each other, that means they are equal and opposite. So let us first calculate the CLSE. We have all the information available to us for calculating CLSE. The formula tangent CLSE is equal to V cos cos divided by 900 cos lat plus V sin cos. We have a positive sign here because the course is 165 degrees true, which is a easterly component course. It's a southeasterly course. Putting the values here, we get the formula 20.6 cos of 15 degrees, 900 cos of 61 plus 20.6 sine of 15 degrees. The course is south 15 degrees east, which is 165 degrees true. The speed is 20.6 knots given to us, and the latitude is 61 degrees south. So when we put these in the calculator, we get the steaming error as 2.580 degrees. The name of the steaming error will be east or low. Now, why is it east or low? That's because the course which we are having, 165 degrees true, is a southeasterly course, has a southerly component. Whenever the course has a southerly component, the steaming error is always east or low. So we have the steaming error available to us now. Now, since we know that the damping error and CLSE are exactly equal and opposite in this case, the damping error will be exactly opposite. That will be 2.580 west or high. So this tells us that the damping error for this particular compass at this particular latitude has to be 2.580 degrees west. And this is the reason why the gyro is pointing due north, because both of these are equal and opposite, cancelling each other. Now we want to calculate the gyro error on a course of 345 true at a speed of 13.3 knots in latitude 61 degrees north. In the first case, the latitude was 61 degrees south. In the new situation, the latitude is 61 degrees north. If we go to the same northerly latitude, the magnitude of the damping error will remain same, but the sign will be reversed. You see, putting the same thing in the formula K tan lat, whether it is 61 degrees south or it is 61 degrees north, the magnitude of the damping error remains same. Only thing is the naming of the error now changes from west to east, because in northerly latitudes the damping error is always east or low. Hence, the damping error in latitude 61 degrees north will be 2.580 east or low. Now moving further, let us calculate the CLSE for the new latitude and course. We have the damping error available now, which is 2.580 east or low as calculated in the last slide. So moving on to CLSE or the steaming error. Tangent of steaming error or CLSE is equal to V cos cos divided by 900 cos lat minus V sin cos. Why negative sign here? Because the course which we have 345 has a westerly component. It's a northwest quadrant course. Whenever the course has a westerly component, we have a negative sign in the denominator. Putting the values, the speed is 13.3 knots. Cos of course is north 15 degrees west. So we use the value of 15 here. 900 cos of latitude is 61 minus V cos V sine course, V is 13.3, sine of course which is 15. Putting these values in the calculator gives us the steaming error as 1.7 degrees west or high. Now, why is the steaming error westerly or high? This is because the course has a northerly component. 345 is a northwesterly quadrant course. Whenever the course has a northerly component, the steaming error is west or high. So we now have both the errors available to us. Damping error is 2.580 east. So we have it here. And the steaming error is 1.7 degrees west. So when we combine both these errors, since they are of opposite names, we will subtract the smaller one from the bigger one. So 2.58 minus 1.0 gives the error as 0.880 degrees. The naming is given of the higher value, higher magnitude, which in this case is east. So the total resultant gyro error is 0.880 degrees east. Now, since the error is 0.880 degrees east, the spin axis will be pointing 0.880 degrees east of north. Thus, the direction of the axis will be 0.880 degrees true. Now, what they have asked in this question is not the gyro error. They have asked us what will be the direction of the axis. To make it little more tricky, they have asked the direction of the spin axis. So whenever the arrow is east, the spin axis will be pointing east of north, that is 0.880 degrees true.
सर ये नहीं समझ में आ रहा है लास्ट पॉइंट.
Ship with gyro compass uncorrected for damping and steaming errors. Steers
सर
200 degrees true and gyro. Go ahead. A ship with gyro compass uncorrected for damping and steaming errors steers 200 degrees true and gyro from position A in latitude 60 degrees south to position B in latitude 64 degrees south. Determine the speed of the ship and the course to steer from position B to A with gyro compass uncorrected. It is given in the question the ratio of PC to PD, control precession to damping precession, is 40:1. In other words, they have provided us with the value of K, which is equal to 1 by 40 in this case. Now this question is little different from the ones which we have done till now. Till now we were given the ship's particulars and we were required to calculate the compass error, but now they want us to find the speed of the ship. So let's see how we go about the solution. Now, as we did in the last question, in this question also, the gyro compass is uncorrected for damping and steaming errors, but it is steering 200 degrees true and gyro. So if 200 degrees true as well as gyro course is being steered, that means the gyro error is nil, zero gyro error. Now, how is that possible for a compass which is uncorrected for these two errors? So that's only possible if both these errors are exactly equal and opposite to each other, thus cancelling out and making the gyro error as zero. So the gyro compass is uncorrected for both the errors, but is steering the same gyro and true course. This is only possible if the CLSE, steaming error, and damping errors are exactly equal and opposite. Now we have the information to calculate the damping error. So let's calculate the damping error first using a mean latitude of 62 degrees south. Now you see the ship is moving from 60 degrees south to 64 degrees south. Whenever the ship is moving, the latitude will be changing continuously, and the damping error will also be changing continuously. So whenever we are calculating the damping error for a particular stretch, we use the mean latitude to get the damping error. So 60 degrees south to 64 degrees south, the mean latitude comes out to 62 degrees south. So using this in the damping error formula, sine of damping error is equal to k tan latitude. K is equal to 1 by 40. It is given in the question. Tangent of latitude, which is 62 degrees, gives us the damping error as 2.695 degrees. Now, since the vessel is in the southern hemisphere, the latitude is south, the error will always be west or high. The damping error is always west or high in the southern hemisphere. Now we know CLSE is exactly equal and opposite to the damping error, since the total gyro error is 0 here. So the CLSE or the steaming error will be 2.695 degrees east or low. Now using this in the steaming error formula, we will get the steaming error formula is tangent of CLSE is equal to V cos course divided by 900 cos lat minus V sine course. The negative sign is because we have a westerly component of the course. The course which is being steered is 200, which is south 20 degrees west. So whenever we have a westerly component, there is a negative sign in the denominator. Now moving on to the second part, we need to know what should be the course to steer if you want to go from position B to A. So for finding the course to steer from B to A, when we are going from position A to B, the vessel was steering 200 degrees true. Therefore, the true course from B to A will be its reciprocal, and that's going to be 020 degrees true. The position A and B are the same. Initially, we were going from A to B on a course of 200. When you go from B to A, you are going in the exact reciprocal direction, and the course also becomes reciprocal, which is 020 degrees true. Now, if we apply the total gyro error to 020 degrees true, we can find the gyro course to steer in this case. Now the damping error is going to remain the same as the vessel is traveling within the same latitudes. So whether you are moving on 200 or you are moving on 020, there is no change in the damping error. The damping error is only dependent upon latitude, and the latitudes are the same. So damping error is going to remain the same. The CLSE will change and has to be calculated. So now we are moving on to the next slide. We will be using this speed 20.81 to find out the CLSE. So beta up to here is
Sir, we
okay.
are
Plus the damping error, which is 2.695 degrees west, giving us a gyro error of 5.301 degrees west or high. Now the true course to steer is 020 degrees true. The gyro is 5.301 degree high. So we add this value to 020. It gives us 025.301 degrees as the gyro course to steer. So we have obtained the second item also. They wanted us to find the speed of the ship and the gyro course to steer from position B to A. Both have been calculated. Steaming error of a gyro on the equator is 2 degrees. Allowing for the same speed and course, what will be the steaming error in latitude 36 degrees 52 minutes? Now this question is a typical question. We have to use a specific formula for solving this question. Let's try to understand the solution. The steaming error or CLSE is given by the formula tangent of CLSE is equal to V cos cos divided by 900 cos lat plus minus V sin cos. Now, if you look at the denominator on the right hand side of this formula, the denominator consists of two components. The first component is 900 cos latitude and the second component is V sin cos. Now the second component, the V sin cos component, is much smaller as compared to the first component. As the speed of the vessel is going to be much lesser as compared to the peripheral speed of the earth. We have cosine of a quantity in the back, cos of latitude here, and here we have sine of cos. The value of cos lat as well as sine of cos never exceeds more than 1. So the deciding factor which decides whether a factor will be smaller or greater is the initial value mentioned here. So in the first component we have 900, which is the peripheral speed of the earth, and in the second component we have V, which is the speed of the ship. Now since the speed of the vessel is going to be much lesser as compared to 900 knots, the second component is much smaller. Now since this component is much smaller as compared to the first component of 900 cos lat, we can get the steaming error or CLSE to a reasonable accuracy even after neglecting the second component. Now, if we neglect the second component, that is the V sin cos component, the formula then reduces to tangent of CLSE is equal to V cos cos divided by 900 cos latitude. So the formula has been simplified now. Now the simplified formula is going to give us a reasonable accuracy because number one, the factor V sin cos was much smaller as compared to the first component. And secondly, the accuracy or the resolution up to which we require this CLSE or the steaming error is only one place after the decimal. So if required, we can use this simplified formula, the reduced formula. Now this being a typical question where there is no indication of the speed as well as the course, we will have to utilize the reduced formula. You see there are too many unknowns in this question. The speed is not known to us. The course of the ship is also not known to us. So these multiple components, unknown components, variables, it is not possible to find using the detailed formula. So we will have to use the reduced formula. So we will be using this formula now to calculate the steaming error. Because if you do not know the method beforehand, if you see this question first time in the exams, it will be very difficult to evaluate and find out that we have to use the reduced formula. But once you have done this, practice this numerical, then you are aware that in case of these kind of questions where there are too many variables, the speed as well as the course both are unknown, we can simplify the formula and use it for easy calculation. In fact, practically on board, whenever we are calculating the CLSE or steaming error manually, we can use this formula very much because it gives us the required accuracy. We only need a accuracy of one place after the decimal. So that much accuracy is very much obtained by using this reduced formula. So clear, beta? Any doubts up to here?